I was once asked by an interviewer, nice fellow, really trying to understand. He asked me to explain magnets. He wanted to know what's happening between these two pieces of metal when you push them together and feel that force. And I have to tell you, I got a little, well, let's say I got a little testy with him, not because it's a bad question, it's an excellent question, but because of what the question really means and what people expect when they ask it. So let me ask you something first. When you ask why magnets repel or attract, what is it you're really asking? What would count as a satisfactory answer for you? You see, that's the problem right there. The answer depends entirely on what you already know, what you're familiar with, and what level of explanation you're willing to accept. Let me give you an example. Suppose your Aunt Minnie is in the hospital. You ask why. Someone says, because she went out, slipped on the ice, and broke her hip. Now, that satisfies most people. Case closed. But think about it. If I came from another planet and knew nothing about ice or hips or hospitals, that explanation tells me nothing. I'd want to know, why do you go to the hospital when you break your hip? Why does ice make you slip? You could say, well, ice is slippery because when you step on it, the pressure melts a thin layer, creating a film of water. Okay, fine, but why does pressure melt ice? Why does water make things slippery? You see how this goes? We can keep asking why and going deeper and deeper until we're talking about molecular forces, quantum mechanics, the structure of H2O molecules. At some point, you have to stop. You have to say, this is where we are. This is what we know. This is fundamental, and that's where we are with magnetic force. Now, I could tell you that magnets attract or repel because of magnetic fields. And you might say, okay, but what is a magnetic field? Good question. A magnetic field is, well, it's the thing that causes magnets to attract and repel. You see the problem? I'm just going in circles. I haven't really explained anything in terms of something more familiar to you. I could try to use an analogy. I could say magnets attract like they're connected by rubber bands, but that would be cheating you because they're not connected by rubber bands. There's nothing physical between them. And if you were curious enough, and I hope you would be, you'd ask me, well, why do rubber bands pull back together when you stretch them? And then I'd have to explain that in terms of electrical forces between molecules, which are the very things that cause magnetism in the first place. So I've explained nothing at all. I've just taken you in a big circle and wasted your time. Here's the thing. Magnetic force is one of the fundamental forces of nature. We have, as far as we can tell, 4 fundamental forces. Gravitational force, electromagnetic force, which includes both electricity and magnetism, the strong nuclear force and the weak nuclear force. These are the bottom. These are the bedrock. Everything else you experience, friction, the normal force when you push on a table, the tension in a rope, the wind pushing on your face, all of these are really electromagnetic forces at the molecular level when you get right down to it. But the electromagnetic force itself, I can't explain that in terms of anything simpler. It's fundamental. It's one of the rules of the game. It's like asking me why chess pieces move the way they do. Well, because those are the rules of chess. If the rules were different, it would be a different game. The universe plays by certain rules, and the electromagnetic force is one of them. Now you might say, but surely you can tell me how magnets work, even if you can't tell me why in some deeper sense. Okay, fair enough. Let me tell you what we know. First of all, magnetism and electricity are intimately related. They're really 2 aspects of the same thing, the electromagnetic force. A moving electric charge creates a magnetic field. A changing magnetic field creates an electric field. They're 2 sides of the same coin. Maxwell figured this out in the 1860s, and it's one of the most beautiful discoveries in all of physics. Light itself is just oscillating electric and magnetic fields propagating through space. Now, where does magnetism in a permanent magnet come from? It comes from electrons. Every electron is like a tiny magnet. It has something we call spin, though it's not really spinning like a top. That's just what we call it. This spin gives the electron a magnetic moment. It's like each electron is a tiny bar magnet. In most materials, all these little electron magnets point every which way. They cancel each other out, so you don't notice any magnetism. But in iron, cobalt, nickel, the ferromagnetic materials, something remarkable happens. There's a quantum mechanical effect, a consequence of something called the Pauli exclusion principle that causes neighboring electron spins to want to line up in the same direction. They all point the same way, and you get these regions called domains where billions of electron spins are aligned. When you magnetize a piece of iron, say by putting it in a magnetic field, you're getting these domains to all line up in the same direction. Now you've got billions and billions of tiny magnets all pointing the same way, and their effects add up. That's your permanent magnet. But here's where it gets interesting. When you bring two magnets close together, the electrons in one magnet are in the magnetic field created by the electrons in the other magnet. And because electrons have charge as well as spin, because they're moving around, there's a force. The details are complicated. Oh boy, are they complicated. But the basic idea is that the magnetic field from one magnet exerts a force on the moving charges in the other magnet. The force depends on the velocity of the charges and the strength and direction of the magnetic field. There's this beautiful mathematical relationship. The force is proportional to the charge times the velocity times the magnetic field, and it points in a direction perpendicular to both the velocity and the field. We write it as F equals Q times V cross B, where that cross means a special kind of multiplication called the cross product that gives you that perpendicular direction. Now, when you push two magnets together with the same poles facing each other, say two north poles, the magnetic fields are arranged such that the forces push them apart. When you bring opposite poles together, north and south, the fields are arranged such that the forces pull them together. The mathematics describes this beautifully. We can calculate exactly how strong the force should be, and our calculations match what we measure in experiments to incredible precision. But notice what I've done here. I've told you about electrons and spin and quantum mechanics and moving charges creating forces in magnetic fields. Have I really explained magnetic force, or have I just pushed the question back one level? Because you could now ask me, why does a magnetic field exert a force on a moving charge? And I'm right back where I started. I'd say, because that's what magnetic fields do. That's the electromagnetic force. It's one of the fundamental forces of nature. You see, at some point we have to accept that there are certain things that just are. The universe operates according to certain principles, certain laws, and we've discovered them through experiment and observation. We've given them mathematical descriptions that let us predict what will happen in new situations. But we can't explain them in terms of something more familiar, because there isn't anything more familiar. They're fundamental. Now let me be clear about something. I'm not saying we should stop asking questions. Far from it. Science is all about asking why and digging deeper. And there are certainly things we can still explain in terms of deeper principles. For example, Einstein showed that electric and magnetic fields are really different aspects of the same thing. They look different depending on how you're moving. That was a profound unification, explaining two things in terms of one deeper thing. And physicists today are trying to unify all the forces. The electromagnetic force and the weak nuclear force have been unified into something called the electroweak force. That's a real achievement, and Weinberg, Salam, and Glashow got the Nobel Prize for it. People are working on grand unified theories that would show that all four forces are really just different aspects of one fundamental force. Maybe they'll succeed, and if they do, then we'd have explained the four forces in terms of one deeper principle. But then you could ask, why does that force exist? And we'd still hit bottom somewhere. The point is, at any given moment in the history of science, there are certain things we can explain in terms of deeper principles, and certain things that are, as far as we know, fundamental. For us, right now, the electromagnetic force is one of those fundamental things. We can describe it mathematically, we can predict what it will do, we can use it to explain everything from why materials are solid to how your computer works. But we can't explain it in terms of anything simpler, anything more familiar. And you know what? That's okay. That's just how science works. We find patterns in nature. We describe them with mathematics. We make predictions and test them. When the predictions match reality, we say we understand that aspect of nature at that level. There might be deeper levels we don't know about yet. There probably are. But at each level, we're limited by what we currently know, what we've currently discovered. Now, here's something that really bothers people sometimes. When I say magnetic force is fundamental, they think I'm saying it's mysterious or magical. No, it's not mysterious at all. We understand it very well. We have equations that describe it precisely. We can calculate the force between two magnets or the force on a charged particle in a magnetic field, and our calculations are correct to many decimal places. That's understanding. That's real knowledge. What I'm saying is that we can't describe it in terms of balls and sticks and ropes and rubber bands and other things you can see with your eyes and feel with your hands. Why? Because magnetic force doesn't work like any of those things. It's different. It operates on its own terms. And that's actually wonderful. The universe is more interesting than balls connected by rubber bands. You know, one of the hardest things for people to accept, and I include physics students in this, is that the world at the very small scale, at the atomic scale, doesn't behave like anything we experience in our everyday lives. Particles don't act like little billiard balls. They're not little balls of stuff bouncing around. They act partly like waves, partly like particles. They're in multiple places at once until you measure them. They have properties like spin that don't correspond to anything spinning in our everyday experience. This is hard for people. We evolved to understand medium-sized objects moving at medium speeds, things like rocks and trees and animals. Our brains are wired for that. But nature at the atomic scale follows different rules, quantum mechanical rules, and those rules are completely outside our everyday experience. There's no way to understand them except mathematically. You can't visualize them in the same way you can visualize a ball rolling down a hill. And I think that's okay. In fact, I think it's beautiful. It means nature is far more imaginative than we are. The universe is stranger and more wonderful than we could have invented sitting in our armchairs. That's what I love about physics. Every time we dig deeper, we find something unexpected, something that doesn't fit our preconceptions, and we have to expand our minds to accommodate this new knowledge. So when someone asks me, why do magnets attract and repel? The honest answer is, that's what the electromagnetic force does. That's one of the rules the universe plays by. I can describe the mathematics of it. I can tell you about electrons and spin and magnetic fields. I can make predictions that you can test. But I can't explain it in terms of pushing and pulling with your hands because it doesn't work like that. It's something new, something different, something fundamental. And if that doesn't satisfy you, if you want to know why the electromagnetic force exists at all, why the universe has these particular fundamental forces and not some other set, well, that's a philosophical question as much as a scientific one. Maybe someday we'll have a deeper theory that explains it, or maybe we'll find that's just how the universe is and there's no deeper why. We don't know yet. That's what makes science exciting. But here's what I want you to take away from this. When you ask why, be aware of what level of explanation you're asking for. Are you asking for a description of what happens? That I can give you. Are you asking for a mathematical framework that lets you predict new phenomena? That exists, and it's beautiful. Are you asking for an explanation in terms of familiar everyday objects and experiences? That I probably can't give you if you're asking about something fundamental. And if I pretend to give it to you using rubber bands or little balls connected by springs, I'm cheating you, because that's not how it really works. The universe doesn't owe us explanations in terms we find comfortable. It just is what it is. Our job as scientists and as curious people is to figure out what the rules are, to describe them as precisely as we can, and to marvel at how strange and wonderful reality turns out to be. And magnetic force, it's part of that wonderful, strange reality. It's one of the fundamental forces that makes the universe work. Without it, atoms wouldn't hold together. Chemistry wouldn't work. You wouldn't exist. It's not mysterious. We understand it quite well. But it is fundamental, and that's okay. That's just how deep our current understanding goes. Maybe someday we'll dig deeper, but for now, that's where we are. And you know what? That's pretty good. We've come a long way from thinking magnets were magic. We've got equations. We've got predictions. We've got a whole technology based on electromagnetism. Your computer, your phone, the lights in your room, all of that works because we understand the electromagnetic force. Not bad for a species of apes who only figured out how to do science a few hundred years ago. So the next time you play with magnets and feel that invisible force pushing or pulling, don't think of it as something that needs to be explained in terms of rubber bands or invisible hands. Think of it as one of the fundamental forces of nature, one of the basic rules the universe plays by. Appreciate it for what it is. Marvel at the fact that we figured out the mathematical laws that describe it. And if you want to really understand it, learn the mathematics, study the physics, dig into the quantum mechanics. That's where the real understanding is. That's all I can tell you. That's as honest as I can be. Magnetic force is fundamental, And that's why you can't explain it in terms of anything else.